Okay, sir. Webinar is now streaming live on Tube. Yes.
Can you see it?
Yeah, I see. I saw it.
Because in my screen it's not. And I opened another one.
Yeah. Please, all the participants, please mute your phones. All the participants, please mute your phone. Mute your phone. And, yes, sir. Yes, sir.
I could able to see up to Vigneshwaran.
Yeah.
After that?
Yes, sir. Don't worry, sir. Please keep, sir.
Okay,
we will manage. Yeah, we will manage.
Okay.
Yeah. Mikael, sir.
Yes.
It's okay.
In my original live stream, it is not streaming.
Okay.
So I'm sending them.
I can saw the icon is live on YouTube. Okay.
Yes, I started another.
Yeah.
Live directly from Zoom.
Yes.
So now that one I'm sending.
Okay, sir.
Them.
After that it is better to add the participants. Okay.
I think participants are there.
Yeah.
Or because it's they can enter without.
So attend is around 150.
Oh, I see. Total?
151 now. Sir, I think it's better to add them. Mikael, sir.
Yes. What should I do?
I think it is better we can add them and starts.
Yes, there are.
It's not working on YouTube.
In this new link, I can write it in the chat, and I have sent the link to those who are in the other stream, which did not start. I don't know why, but I'm sending them to the link which is working.
I think you are creating in another link.
Yes.
But then you send it to my WhatsApp. I will send to the group.
I'll write it in the chat. Let's see. I should be in the right software.
Sir, some of them received the new link, sir.
Yes,
Okay.
I have.
Yeah. Now I pass it to the WhatsApp groups. Okay.
I sent you in this chat. I made the link, and also I'm sending you the email, and I will send you.
Sir, I got it, sir. I got it, sir. I got it. So now this group is working. I think this one is working, sir. Sir?
Yes, so there is 53 watching on the new link.
What, sir?
There are now 65.
Yeah. Okay, sir. Sir, better to add the participants, sir.
Yes, but I think they are there.
So kindly mute all the.
So where do I mute all participants?
Yes, sir.
Do you know where? Oh, here.
Sir. Right side.
So I think in this webinar, it should be participants will not be able to hear. Can you hear me?
Here, sir. Here, sir. Here. Sir, kindly mute all the participants and allow them.
Yes, I think all the participants are muted from the beginning because it's a webinar. So it's only panel who have.
Okay. Let us start, sir. Shall we start?
I think we can start. We can ask.
What, sir?
Me, sir? Hello? Saiju?
Yes, sir. 1 minute. What, sir?
Okay.
Mikael, sir. Mikael, sir.
Yes, sir. Yeah.
Sir, what we will do?
I think we can start because now participants are entering and then I think they can hear us.
Sir, Mikael, sir.
Yes.
Sir, we can add these participants in this platform.
They are in the platform. So there is 150 participants.
They are in the platform now.
Yes, they enter automatically. There is no. So once they follow the link,
Okay,
they are
then
there.
one thing we will do. We can start our webinar, sir.
We can start, yes. So
you
they
you
confirm.
just share me as a host. You just share me as a host.
Okay.
Okay.
So you are host now and participants are there and it is streaming on YouTube. Sir. There's 76.
Start,
yes. So it has.
Yes.
Okay. Sir, can you? Oh, good morning to all participants. The whole world is affected by the pandemic COVID-19. People run restlessly without knowing the remedy, whether he's a career or not. So, still we have to step ahead. A new normal life. Virtual gatherings enabled by various digital platforms are helping socially distant people across the world to engage with one another. Even this in present scenario, it is indeed a matter of pleasure to present today's international webinar on Nanoscience 2020. Next, this pandemic situation, restless situation. Let us start our today's international webinar with a prayer song and be with a song, Showers of Blessing. All we are with that song, we can get the support from the Almighty.
There shall be showers of blessing. This is a promise of love. There shall be seasons refreshing, sent from the Savior above. Showers of blessing, showers of blessing we need. Mercy drops round us are falling, but for the showers we plead.
There shall be showers of blessing, precious reviving again. Over the hills and the valleys, sound of abundance of rain.
Showers of blessing we need. Mercy drops round us are falling, but for the showers we plead. There shall be showers of blessing, send them upon us, O Lord. Come to us now a refreshing, come and now honor thy word. Showers of blessing we need. There shall be showers of blessing, showers we need. There shall be showers of blessing, oh that today they might fall. Now as to God we're confessing, now as on Jesus we call. Showers of blessing we need. Mercy drops round us are falling, but for the showers we plead. There shall be showers of blessing, if we but trust and obey. There shall be seasons refreshing, if we let God have his way. Showers of blessing we need. Mercy drops round us are falling, but for the showers we plead. There shall be showers of blessing. This is a promise of
Next, I would welcome all the participants. I am Lieutenant Dr. Shaiju GJ, Head of the Physics Department, Christian College, Kattakada. Now I welcome all the participants, our colleague chairman, Most Reverend Dharmaraja Rasalam, the moderator of South Kerala Diocese. I welcome the Honorable Manager, of Christian College, Kattakada, Dr CR Godwin, the Honorable Principal, Dr Vincent Joy, sir, and the Staff Council Secretary, Dr SV Shalini, and all other resource persons, especially the supporter of this seminar, Dr Nasar Ali, NANOSMAT from UK, and our resource speakers, Prof C Sanjeeviraja, sir, Dr Mikael, Dr K Jaydeepan, and all the participants. You are the successful of this webinar. I extend my hearty welcome to all on behalf of Department of Physics, Christian College, Kattakada. Next, we can hear the blessed message from the college manager.
Respected Principal Dr. Vincent Joy, our Chief Guest Dr. Nasar Ali, our resource persons, its coordinator and organizer, Lieutenant Dr. Shaiju, conveners, organizing committee members, and beloved students. Indeed, it's a privilege for me to felicitate this very important and meaningful two-day international webinar on nanoscience. I'm so glad that it is organized by Department of Physics of Christian College, Kattakada. Last year, we had an international seminar and it had a great success too. Although the spread of COVID-19 has prevented us to come together and have a seminar, so we switched onto a webinar. We are using this as an opportunity to enter the limitless world of cyberspace and spread our wings to become smart teachers and students beyond borders. I appreciate Dr. Shaiju and all our professors and the whole physics department for taking this initiative to make this happen. And its subject is also very interesting and informative. Nanoscience is an emerging area of science which involves the study of structures and materials on an ultra small scale. Its motto is very interesting: thinking big, working small. Nanoscience and nanotechnology brings out drastic change in the field of food security, energy production, medical field, environment, textile industry, and cosmetics, etc. There are lots of studies going on regarding how to prevent coronavirus by using antiviral surface coating. However, we hope that nanoscience and technology will bring out some solution in this area. Anyway, I am sure that this webinar.
Thank you, respected Achan, for his valuable, motivating message. We are very happy you are from the physics background. Achan, we are extend a hearty thanks for your valuable words, Achan. Next, we can hear a few words from our college principal, Dr. Vincent Joy.
The Department of Physics is organizing 2 days international webinar.
I think you need to share the screen for the video. I see the desktop.
Nano means the particle size is equal to 10 raised to minus 9 meter. When we reduce a material in nano, the whole property of the particle changes, which means the electrical, optical, and magnetic properties change. Now, the human beings are used these property changes in the various daily purposes. Now the gigantic electronic devices reduces its size in nano forms. I congratulate the Department of Physics for organizing this two-day international webinar. Especially I am congratulating the faculty members and its HOD, Dr. G.J. Shaiju, for organizing such a wonderful event. Thank you.
Sir, thank you for your valuable supports and freedom to move the physics department ahead. Thank you very much, sir. Next, Dr. Nasar Ali, sir, the founder and chairman of NanoSMAT, executive committee member, and he is the founder of Young Speakers Club internationally, NanoSMAT, the Manchester Metropolitan University, United Kingdom.
Please
Just
also
we can
check,
hear-
excuse me.
We can hear the motivational message from Dr. Nasar Ali, UK.
Can you hear me, Shoji?
Yes, sir. Here.
I think start video first, and then you share the video, because
A
now
very
I
good
have seen the
morning to
desktop.
everyone.
Now
My
it's
name
clear,
is
sir?
Dr.
Now I see
Nasar
the
Ali,
desktop.
and I'm speaking here from the
It's okay, sir?
NanoSMAT office based here in
No,
Manchester
I don't see
in
video.
the United Kingdom. And it's a
see.
glorious day here today in Manchester. The sun is out and the temperatures
So you can
are
see?
in the
Not video.
mid-20s. And I'm sure this is nothing
Only
compared
voice.
to the summer days in India. However,
So
What's that?
if you start the video first and then share the screen to the video, because I could now see the desktop and hear the voice, but not video.
Okay, sir.
Start video
I
first.
too. No video.
So if you start the video first and then share screen to the video.
Now, okay, sir.
Now it's desktop again.
You can hear? Okay.
Now there is no,
a very good morning to everyone.
Now, okay.
My name is
Now I can
Dr.
hear, but
Nasar
no
Ali,
video.
and I'm speaking here from the NanoSMAT office based here in Manchester.
so if you start the video first and then share screen, so stop sharing and now you start the video.
Start the studio. Now it's okay. Now it's okay, sir.
I don't hear anything yet.
You can hear?
No,
Now, okay.
no, I cannot hear video. Maybe if you start video and then share the screen, then maybe also the sound will come.
So now it's okay?
A very good morning to everyone.
Yes.
My
Okay.
name is Dr. Nasar Ali, and
Sir,
I'm
is it
speaking
okay?
here from the
It is okay.
NANOSMAT office based here in Manchester in the United Kingdom. And it's a glorious day here today in Manchester. The sun is out and the temperatures are in the mid-20s. And I'm sure this is nothing compared to the summer days in India. However, we are trying to enjoy this good weather, but we are still officially in lockdown in the UK due to the COVID-19 situation. And I would like to take this opportunity to welcome everyone to this two-day international webinar on nanoscience. Now, these webinars will become a lot more important now, especially due to this COVID-19. And surely this will have an impact on the world and how we live our lives and how we conduct our businesses and how we go on about living our lives. And distance learning and doing work over the internet is going to play a bigger part now in our lives. So it's a very good initiative from the Christian College to organize this two-day international webinar on a very, very important topic, nanoscience and nanotechnology. So I congratulate the Department of Physics, Christian College for organizing an excellent webinar, and I'm sure you will all find it very, very beneficial. And now we have these good technology, sophisticated, advanced technologies platforms which allow us to conduct these meetings. Also, I would like to say a few words of thanks to my colleague, Dr. Syväjärvi, who is currently the head of the physics department. Dr. Syväjärvi I met in 2011, 9 years ago, when I was involved with and chairing a international conference on nanotechnology, the NANOSMAT conference in 2011, which was held in Krakow in Poland. And I was very pleased to meet him. I listened into his presentation and we established a friendship. And since then, we have been regularly in contact. And I was very, very happy and pleased by his personality. He's an extremely kind person. And we know that if you're kind to others and if you do good, good comes your way. So earlier this year, when I found out that he was promoted to lead the physics department, I was very, very happy for him. And I'm sure that under his leadership, the department will do extremely well. So this webinar is being organized by the physics department, and which is part of Christian College, which is affiliated to, I believe, the University of Kerala. And it is very important that we actually, as I mentioned earlier, that we continue to work on science, because science is very, very important, and especially nanoscience and nanotechnology, which has huge potential. So even if we look at this current climate that we're in due to the COVID-19, in a lot of the countries, I know in the UK they were saying that it's science must dictate what happens when we go into lockdown, when we come out of lockdown, and also how to overcome this COVID-19, this virus. So therefore, there's a lot of efforts now being done all around the world. I know there's groups in Oxford University, a lot of people, scientists in China, in Germany, in the United States are working on developing a vaccine which will get rid of this virus. So scientists must continue to work even though the world may be in a lockdown due to COVID-19. So as I mentioned, this is an excellent opportunity, and I'm sure the scientists will work together on very, very important topics in order to see if they can overcome some of the challenges that face us as a global community. So I wish you all the best, all the best, and I hope that you're keeping safe during these very difficult and unprecedented times. And but we need to be very optimistic. We need to be very positive. So therefore, we need to have this positive approach in life and continue to work, whether that might be working from home or so, working with these special social distancing measures that we may need to incorporate in our lives from now on. So once again, welcome to this two-day international webinar, and I hope you found this very useful, very productive. And even at NanoSMAT, we are creating an institute now which will be involved in distance learning, e-learning. We have a webinar on innovation on the 17th of June. I have my colleague Mikael from Sweden who will be giving this webinar on innovation, how you can translate the work you do in the lab scale and translate it into innovation and to which could lead to startup companies. And Mikael will also be speaking later today on his research, so I'm sure you will find that very useful. So in the meantime, thank you very much and have a great webinar. And I look forward to interacting with you and with you after this conference, after this webinar, and also in our future NanoSMAT program.
Thank you, sir, for your support for the international webinar. We are very much thankful to you for your support. We need your future support also, sir. Next, the time is too late, but even though only one program is there, the next week, our Staff Council Secretary say a few words as a felicitation.
The Department of Physics has decided to conduct 2 days international webinar on the topic of Nanoscience 2020. On this occasion, as a Staff Council Secretary, I wish to congratulate the Department HOD, Lieutenant Dr. Syväjärvi. The Department of Physics has decided to conduct 2 days international webinar on the topic of Nanoscience 2020. On this occasion, as a Staff Council Secretary, I wish to congratulate the Department HOD, Lieutenant Dr. Syväjärvi, and all other faculty members. Thank you.
Now we are very eager to hear the session of Prof C Sanjeeviraja, sir. He's the, now we have the time about, I think, 12:15, 15 minutes, we are late. But even though he can able to extend his talk up to 1:15, don't worry, sir. He's a very eminent person. Especially, he was the Dean, head, as a professor in Alagappa University, Karaikudi. Now he is working in the Government Engineering College, EC department. He's an emeritus professor. Visit a lot of countries, and he's very he's motivating me a lot in research works. When I was doing my PhD, he was my work supervisor. He provided me all the facilities in his lab. I do my research and I took my characterization by using all the instruments in that particular lab. Characterization, especially XRD, AFM, photoluminescence, UV vis, etc. All the characterization that took my work. So my supporting sir, I'm very pleasant to introduce you in this big participants. Now I welcome you, sir, to handle the lecture section 1. Thank you, sir.
Okay, thank you. Thank you. Shall I go to share screen?
1 minute, sir. Yes, sir.
Is it visible?
Yes, sir. It's visible.
Okay. Okay, I thank the organizer.
So please, it starts from the first slide, sir.
First slide.
Yeah, from the beginning.
Okay.
Okay, sir. Now you proceed. Sir.
Okay, but I could not able to see the screen.
Now, but we can see, sir. We can see.
Okay.
Right.
Shall I
You can
proceed?
proceed. Yeah, proceed, sir.
Okay.
Okay.
Thank you, Dr. Syväjärvi, the organizer of this Nanoscience 2020. And also I thank the organizer. And is a right time to discuss about this nanoscience. Is a right time, and under this title I am going to present nanomaterial preparation techniques. Okay, what is nano? You may raise a question. And without materials, we cannot able to speak science. Therefore, nano is nothing but a very small size. The size will be in the order of 2000, in the order of 10 power minus 19 meter, and the materials is nothing but various materials can be prepared. There is oxide materials or semiconductor materials or any type of material can be prepared in the form of a powder, and that powder can be used for device fabrication. And my talk is my objective of my talk is nothing but brief introduction about your nano materials and nanoscience, and also the application of your nano materials. And then we will move to the preparation techniques. We can categorize the techniques into two types. There is a physical route and chemical route. And the physical route we can form in the form of a thin film. Of course, nanomaterials will be prepared, and that materials can be used for the device, and the device usually in the form of a thin film. Therefore, physical route will give a thin film form, and that too for nanomaterials. And in chemical route, that is, we can prepare our powder in the form of a nano size, and also for device fabrication, we have to prepare a thin film using these nanomaterial. Therefore, we can see some of the techniques is under chemical route. And finally, we can see the confirmation of size. Here we are talking about nano size, and how we can measure nano size. And here I am going to discuss only two techniques. One is X-ray diffraction, and another is transmission electron microscope. Finally, I will conclude my talk. That's all. Are you able to see that slides, Syväjärvi? Hello?
Yes, it is seen. So on Zoom
Okay,
and
okay.
also on YouTube.
I can see. Okay,
Can I continue?
Yeah, here
Yes,
you.
please.
Okay, you proceed, sir. Don't worry.
Okay.
Proceed.
And
Yeah.
brief introduction about your nanomaterials. And you may raise the question, what are nanomaterials? New class, it's nothing but a new class of materials. Astronomic properties and potential applications. There's a lot of applications using these nanomaterials. There can be metals and ceramic, polymeric materials, or composite materials. Any type of materials can be prepared in the form of a nanomaterials. It is a very small size in the range, 1 to 100 nanometers. Probably you can extend the size also. For example, 1 to 150 or 1 to 200 nanometers. Nanometers can be represented as a nm. Nano is from a Greek word, and it means drop or extremely small. 1 nm spans nearly about 3 to 5 atoms lined up in a row. I will give an example for this particular one in a diagrammatic manner. And the importance of this nanomaterials is nothing but materials are especially strong, hard, and very tactile and at high temperatures, wear resistant, corrosive resistant, and chemically very active. These are some of the important properties regarding that nanomaterials. And they are also much more formable than their conventional, commercially available counterparts. If you take a commercial bulk material, we cannot have such properties. When you prepare the same material into a nano form, then the properties are enhanced. Nanomaterials research literally exploded in mid-1985 by US. And here are some of the examples. And these, for example, if you take an atom, the atom is nothing but a few tenths of a nanometer, is less than nanometer. If you take a nanometer, then DNA molecules are about 2.5 nanometer wide. Suppose if you take, there are 10 hydrogen atoms solder to solder, that will give you about 1 nanometer. And thousands of nanometers, example for blood cells, is nothing but thousands of nanometers. If you take an ant, and the ant is millions of nanometers across. And if you have take a human being, of course, billions of nanometer, of course, a 2 meter height of a human being, nothing but billions of nanometer. And here you can see the pictorial representation, atom, the center nucleus, we can electrons are revolving. Therefore, the size will be in the order of 1 angstrom. It is less than 1 nanometer. And if you take a 1 nanometer order, that is a DNA, and proteins will be in the order of 10 nanometer. If you take a virus, even if you take a COVID-19, the size will be in the order of 150 nanometer. And if you take a cell, that is in the order of 1 to 10 micrometer. And during 1970, silicon transistor size will be in the order of 10 micrometer. But at the same time, around 2003, silicon transistor size will be 0.13 micrometer only. Now it is still smaller in the nano world. And if you take a table, for example, if you take a hair width of a human being, this will be in the order of 50,000 nanometer. Red blood cell is already I mentioned 7,000 nanometer. Bacterium nearly about 1,000 nanometer. Virus will be in the order of 100 nanometer. If you take a width of a DNA, it's a 2.5 nanometer. Aspirin molecule will be in the order of 1 nanometer. And if you take a carbon, is a very good example for nanomaterials. And here carbon nanotubes and vacuum balls, these are all some of the examples. And you are going to hear this lecture in the afternoon by Professor on graphene seeds. And if you roll the graphene seeds, then you can have a carbon nanotube. And these are some of the important examples, and also very good example for nanomaterials. And some properties of a carbon nanostructures is a high tensile strength, physically stable, chemically reactive with free radicals, and other atoms can be placed inside its catch. That is another advantage. And you can put a material inside that vacuum balls, and then we can change the property of that one. And these are some of the nanocarbon structures. For example, C60, C70, onion, endohedral, and single-walled nanotube, multi-walled nanotube, and fullerenes, etc. These are some of the materials based on carbon. And these are very good example for drug development, and biological nano devices based on tendermits are being developed with a potential to recognize cancer cell and diagnose the cause of cancer cell and delivery of a drug to target. For example, cancer cell will be there in a particular location, and you can very well target that particular cancer cell by this particular nanomaterial and report outcome of therapy. And we can have we can take the data from the cancer cell up to a particular depth. And if you take a nano sizing of drugs, these are some of the important potential applications of our nano sizing drugs. Increase surface area, enhance solubility, increase the rate of dissolution, increase oral bioavailability, more rapid onset of therapeutic action, and decrease the dose needed. For example, we can reduce the dose level of medicine and decrease the fat and phosphate variability and decrease patient to patient variability. These are all some of the important potential application of nano drugs. And what are nano means? Already I mentioned, and this nano in nanotechnology is often thought of as a shortened form of a nanometer, is a nm. And even if you take a human hair, I already have mentioned, these are nano fibers, and these are nano hair. It's a hair, human hair. The length is a diameter of the hair will be in the order of 10,000 to 80,000 nanometers. And how we can produce the material, nanomaterial. These are some of the important wide preparation techniques. That is a salt synthesis, inert gas condensation, mechanical alloying or high energy ball milling, and this especially for ball milling, top-down approach, and plasma synthesis and electrode deposition. These are all some of the important nanomaterial synthesis is throughout the world they are doing like from this particular technique. And here we are going to see only physical and chemical route, especially that sol is under chemical route, and that I will explain in detail. And these are some of the other forms of your nanomaterial. Is a nanotube, for example, this is a nanotube or nano wire and nano seeds. We can have a nano seeds, nano cone, and for example, these characters shows new functions unseen in the bulk substances. You cannot able to see these functions in bulk material. Improving function to a great extent. Of course, improve the function of the material. Function of the material means properties of the material can be greatly extended. And substances for the next generation. Of course, we can say these are all the substances for the next generation of a human being. And these are the other materials is nano clusters, nano precipitate, nano crystals. For example, these are all nano crystals. This is one crystal, this is another crystal, this is another crystal like that. And the size will be in the order of a nanometer. Therefore, we can call this a nano crystal. Nano composite. There are two types of material here, red and black. And the red correspond to one type of material, black correspond to another type. For example, this is one nano crystal, this is another nano. For example, this is A and B, and the size will be different for this. And therefore, this is a composite. Composite means it's something but combination of one or two material. And but it will all react with one to another. For example, this is a separate one. The property of your red correspond to one property and black correspond to another property. Therefore, combination of two properties can be achieved through your nano composite. And if these two are react, then that is called compound. And here it is amorphous material. There is no arrangement here. Therefore, we can able to prepare amorphous nanomaterial. And if you take your amorphous and also nanocrystalline, for example, this is a crystalline and red color correspond to your amorphous material. There's no arrangement for red, but there is an arrangement for your black, and that is called nanocrystal. Therefore, combination of your amorphous and nanocrystals. And here nanocranulars, for example, if you put these material on your substrate, we can have a nanocranulars. And if you prepare a material, nanomaterial, one layer to over another, for example, is a violet, red, and violet, red like that. These are all layers of your nanomaterial on any particular substrate. And these are some of the applications. We can prepare our nanomaterial in this particular various form. These are some of the examples of our on the left hand side, and another is the right hand side. I can show the example of material or applications, and the size is also given in the center. The size will be in the order of 1 to 100 nanometer. If you take a nano tube, and diameter will be in the order of 1 to 100 nanometer. And if you take your nano wires, again it is in the order of 1 to 100 nanometer. And of course, if you see that applications, it's the metals, semiconductors, oxides, sulfides, nitrides. These are some of the material, and these material can be widely used in your devices. Suppose if you take your nitrides, we can have very well for your hard coatings, titanium nitride, aluminum nitride, titanium aluminum nitride like that. And if you take a dye, it's a nanotubes, even we can use this as a material for contact and other things. And these are the important physical properties of our nanomaterial. It is having a lower melting point and lower phase transition temperature. Normally in bulk form, the transition temperature will be higher, but the same material can be prepared in the nano size, and it is a phase transition temperature will be lowered. And mechanical properties can reach the theoretical estimate. Actually, theoretician can estimate a particular result, for example, Young's modulus or like that we can have, and that particular theoretical value can be easily approachable to your nanomaterial. Almost 1 or 2 orders more than the bulk we can able to achieve. It will approach the theoretical value. This is due to reduced defect concentration. Therefore, in your nanomaterial, there is a defect concentration level will be very, very low when you compare to your bulk material. And other properties like optical, if you take optical properties significantly different. For example, in semiconductor nanomaterial, blue shift will be there. For example, if you prepare your material and if you take your absorption edge, the absorption edge is shifted to blue side, then there is a blue shift, we can call it. And in that case, what will happen? Your material is in the form of a nano, and the band gap is also changed towards your lower wavelength. And according to your convenience or according to our device requirement, we can tune our material to a particular band gap by adjusting the various preparation techniques or preparation parameters. And electrical conductivity, if we take, so decreases due to is a small size, so scattering is a scattering of our electrons. That's why the conductivity decreases. For example, if you take a metals and for metals, nanometals will have a electrical conductivity will be decreased. And at the same time, if you take a semiconductor, it will be increased. Magnetism will be distinctly different. Ferromagnetism can appear or disappear on nanomaterials. In general, almost all these properties depend on the size of the materials or size of the particles. And in other words, properties can be tuned by adjusting the size, shape, and extent of our agglomeration. For example, this all how can these properties can be used to protect the environment. For example, the nanomaterial can be widely used for your catalytic property, can be used for better catalytic efficiency through higher surface to volume ratio and electrical measurement or electrical devices and magnetic devices, mechanical devices, optical devices, spherical, biological. Therefore, in order to, apart from that, there is a wide application in medicine also, and medicine and environment also. And here I have given an example. Increased electrical conductivity in ceramic and magnetic nanocomposite, increased electrical resistance in metals. Like that, we can have our material according to the properties. And this is a diagrammatic representation of characterization of our material. Now we can see the preparation of our nanomaterial with a different route. There are two routes here I am going to discuss. One is a physical route and another is a chemical route. And physical route is nothing but vacuum evaporation and reactive evaporation and electron beam evaporation, sputtering, and hot wall vacuum evaporation, pulse laser deposition, molecular beam evaporation. Of course, it's a versatile one, and the other things we can able to discuss. For example, if we take our vacuum evaporation and we can transport our material, or we can transport the elements or atom or molecules in your vacuum level. There is a medium, there is no medium at all. Through that medium, there is without any air molecule, and your medium should be a vacuum. In the vacuum medium, we can transport the ions or either element or molecule or ions. And then we can sublimate that, or you can condense that ions or atom on any particular pre-cleaned substrate. Then we can have a very good thin film, and thin film material is nothing but a nanomaterial. And in another route, we can call it a chemical route. Therefore, we can classify into two routes. One is physical route and another is chemical route. In chemical route, salt gel chemistry, either we can prepare thin film or a powder through salt gel, spray paralysis, and it's a very simple technique. We can prepare our nanomaterial in the form of thin film and nebulized spray paralysis, spin coating, and spin coating is something but you can spread your solution on any particular substrate and then rotate it, and then we can able to have very good thin film. And the materials are all nano size. And electrochemical method and chemical method and combustion synthesis, chemical self-assembly, and etc. And these are all some of the chemical route I am going to discuss up to is combustion synthesis. First, we will see that physical vapor deposition. And physical vapor deposition process or film deposition process only. And actually, this is a vacuum. You can assume this rectangle shape is nothing but a vacuum chamber, and the vacuum chamber should be evacuated by different types of pumps like rotary, diffusion, or turbomolecular pump. And through that, we can able to create the vacuum level up to the 10⁻⁶ torr in laboratory. For industry and for device fabrication, the vacuum level will be in the order of a 10⁻⁹ torr. And room atmosphere is nothing but 1 torr, and you have to reduce the pressure, or we have to evacuate the air inside the chamber by various vacuum pumps. Then once if you reach the vacuum level up to 10⁻⁶ torr, then you can put your material, for example, source material is nothing but a bulk material, to be formed into nano size. And for example, you can take a cadmium sulfide, and in that case, cadmium sulfide should be loaded inside that chamber, and pre-cleaned substrate should be loaded inside the chamber. Once if you loaded the samples and the substrate inside the chamber, then you can apply some very high temperature to your source. That high temperature can be achieved by putting a helical element, helical tungsten element, or board, molybdenum board or tungsten board can be taken. And if it is a board, you can put your sample about a few milligram in your board, and you can board is having two ends, and one end you can put a plus end, plus voltage, and another side you can put a zero voltage or negative voltage, and through that you can apply about hundreds of amps, and voltage will be in the order of a 6 volt. Then very well your filament or your board will glow, and we can reach the boiling temperature of your source material. Once it reaches that boiling temperature of the source material, the vapor should be created inside the chamber. These vapors will be traversed in all directions inside the chamber, and the mean free path length will be in the order of 30 or 30 centimeter or more than that, even more, 1 meter also. And in order to have our 1 meter mean free path length, you have to reduce the vacuum level. That is very important. That is why you have to create our chamber up to the level of 10 power minus 6 torr, or better than 10 power minus 6 torr. And once the vapors once the vapors are traversed, and you can put your substrate just opposite your source material, immediately these material or atom or molecule will deposit on your substrate. The substrate is already clean, pre-cleaned, and your material will be first nucleation will be formed on the substrate surface. Slowly the cluster will be formed, and then your crystalline material will be grown, and then a shape of your crystalline material will be there, and similar crystallines will be spread throughout your substrate. Then you can have, if you measure the crystalline size will be in the order of a nanometer through that through vacuum evaporation. And if instead of a vacuum, if you put your any reactive gas inside, then that is called reactive vapor evaporation, reactive thermal evaporation. Okay, that is called your thermal evaporation. And the next technique is something called electron beam evaporation, and it's also done inside the vacuum. And again, you have to create your vacuum chamber. The pressure level will be in the order of a 10 power minus 6 torr or better than that, and you can load your material. And here I am going to use only electron, highly accelerated electron will bombard your material, and that kinetic energy will be converted into heat energy. That heat energy will be utilized by your material or the source material, and the source will be in the form of vapors. And the main advantage of your electron evaporation is, and here you can load a few milligram of sample is sufficient rather than your thermal evaporation. Therefore, small amount of your material will be vaporized, and these materials will be deposited on your substrate. Again, the substrate is a pre-clean. In order to have your uniform coating or uniform nano material, you can rotate your substrate in a particular speed, and your substrate and source material should be face to face, and therefore these are conical shape. Divergence will be there, or your vapors will be traversed by conical shape, and you can put your substrate just opposite your source material, and your material will be formed in the form of nano size and also arranged in a plane. And here, how we can accelerate electron? You may raise a question. Here you can apply some very high potential, and or we can say you can take an anode, and below that anode you can put small element is that to produce thermionic electrons. And here there is a filament, tungsten filament. You can apply very low voltage and very low current. Current will be in the order of milliamps, and voltage will be in the order of 6 to 12 volt. Once if you apply a voltage and current, and filament will glow, and thermionic electrons cloud will be there around the filament, and these electrons will be attracted by anode, and at the anode is nothing but a plate. At the center there is a hole. Through that hole, these electrons are traverse directly or from a straight line, and these electrons again converge, or you can divert by putting magnetic field perpendicular to your electric field, and your electron will travel in third direction, and or in a circular path, you can abruptly stop by putting your material in the particular electron path. Immediately that kinetic energy will be converted into your electrical energy by hitting that material, and vapors will be created. That is called your electron beam operation. This is a major difference between thermal evaporation and electron beam operation. And if you take a sputtering, another is a schematic diagram of our vacuum chamber in our laboratory, and this is a vacuum chamber, and inside the chamber you can load your substrate, and this is where material to be formed in the nano size. And for example, you can take a cadmium sulfide or any material, metal or compound, and you can take what a particular material will be evaporated and it will be deposited. Therefore, the vacuum chamber you have to take. In industry, the chamber size will be very, very, very large. And even a 1 meter or 1.5 meter height, and the diameter will be in the order of 1 meter. And for laboratory purpose, this diameter will be in the order of 30 centimeter. And of course, these are the pumps, rotary pump and a diffusion pump. These two pumps are used to evacuate the chamber, and you can, in order to monitor the pressure level, you can put your thermocouple gauge and also ionization gauge. These are the two gauges to monitor the pressure inside the chamber. Okay, these are all some of the valves to control, or either you can open or you can close. And this is a schematic diagram of any vacuum system in our laboratory or in any laboratory. Okay, this is the sputtering technique, and this is your chamber. The rectangular one is something but a chamber, vacuum chamber. Initially, you have to evacuate the chamber. The vacuum level will be in the order of 10 power minus 6 torr inside the chamber. And here you can put your material, or material means material in the form of a bulk. Bulk is nothing but a disc. You can put high purity disc. Suppose if you want to evaporate tungsten oxide material, you can take a tungsten oxide target. The target size will be in the order of a 2 inch, or you can have a 3 inch, depending upon your sputtering system. And this is where material to be synthesized into nano form. It is in the bulk form. Then during your, after sputtering, we can able to prepare our nano size material. And this is a substrate. And above the substrate, you are going to have our nano material in the form of a thin film. Okay, the whole thing, you have to put it in your chamber, and you can apply very high negative potential for your target. And inside the chamber, initially the vacuum level will be in the order of 10 power minus 6 torr. Then you have to introduce your sputtering gas, like inert gases. For example, argon. Argon is a very good example for inert gas. And why we have taken inert gas means it will not react with our material, target material. And that argon ions usually ionized. That's why people are using argon gas. Or you can use nitrogen. Suppose if you take a nitrogen, you have to be very careful. And sometimes nitrogen will react to a target material or a source material. And in that case, we cannot use that nitrogen as a sputtering gas. Therefore, argon is a very good example. Most of the people will be using argon gas, and that argon gas easily ionized. For example, initially you have to put a very low voltage, and during that voltage between, for example, substrate is holded by a plate, metal plate, and target is fixed on another metal plate. And these two are connected to your power supply. And when you apply very high negative potential between these two, and your argon ions will be ionized, and here it is a negative potential. Therefore, what will happen? These ions are attracted towards this particular direction, towards the top. Or top, what will happen? We are having a target material or bulk material. And that bulk material, what will happen? Because of the bombardment, ion is argon ion is a very heavy ion, and a heavy ion means, and it is having a velocity also. Because of that, you can have a very high kinetic energy. And that kinetic energy is more than that binding energy of your material to be vaporized or to be prepared as a nanomaterial. Therefore, this argon is bombarded, and mechanically we can remove your ions, or mechanically you can remove your atom. For example, if you take a tungsten target, then tungsten atom will be removed from the target. And or if you take a tungsten oxide molecule will be removed from the target, from the surface. Therefore, what will happen? These argon will be bombarded, and your either atom or molecules will be released from the target, and these molecules or atom will be deposited on your substrate. And you can have, for example, in order to have our very good nano material, we can apply some very low temperature also. For example, 50 degrees centigrade or 100 degrees centigrade. If you prepare your material on room temperature, most of the time we are having only amorphous nature only. There is no nano material. Therefore, you can rise a substrate. The substrate temperature will be in the order of 100 degrees centigrade or 500 or any, you can, according to your convenience or according to your requirement, you can put your temperature also in your substrate. And in order to have our uniform coating, you can rotate your substrate. And like that, we have to do. Therefore, when you introduce your argon gas, now the pressure inside the chamber will be in the order of 10 power minus 2 torr only. Initially, the vacuum level will be 10 power minus 6 torr. And if you introduce your argon gas, sputtering gas inside this chamber, we can, if you measure the pressure inside the chamber, the pressure will be in the order of 10 power minus 2 torr only. And in addition to argon, for example, I have taken our tungsten or titanium target as a target material, and I want to prepare titanium nitride as a nano material on your substrate. In that case, you can take your titanium target. The target size will be in the order of a 2-inch dia, and you can introduce nitrogen as a reacting gas. Therefore, titanium atom and nitrogen will react, and a compound will be formed. This a titanium nitride will be formed, and that will be deposited on your that will be formed on the substrate in the nano size. And that is a reactive sputtering. That is called DC supply is applied. And once if the target is a ceramic target, there is insulating target. Sometimes we may require insulating material. And in that case, instead of a DC source, you can replace with the RF source, radio frequency source. Then that is called RF sputtering. And in that RF sputtering, what will happen? The frequency will be 13.5 megahertz. Therefore, what will happen? The clouds. These electron clouds will be formed around the target. That will be dispersed, and a more efficient way we can able to operate or prepare on your substrate when you take your RF sputtering. Therefore, if you take again, the process is the same. There is initially you have to evacuate your chamber, and you have to remove your air inside the chamber. The pressure inside the chamber will be in the order of a 10 power minus 6 torr. Then you can introduce argon gas. Then you can put your target here, whether it is a metal or insulator or semiconductor, and you can apply the RF power. And depending upon the power, you can have that particular either 50 watts or 100 watts, depending upon the binding energy of your material. You have to have you have to monitor, or you have to synthesis, or you have to set the voltage RF power in your supply. And in that case, we can have a very good nano material on the substrate. And instead of, in addition to argon gas, if you introduce your nitrogen for I want to have a titanium nitride, then titanium nitride will be formed. Or if you put a tungsten, then tungsten nitride will be formed. Like that, you can have. You can introduce your is a reactive gas, then that is called reactive RF sputtering. Okay. Instead of that, if you introduce a magnetic field here, there is in your target, you can put your magnetic field here, and in addition to your electric field, then that is called is RF magnetron sputtering. Therefore, there are different techniques are there. RF sputtering, RF magnetron is a DC. If suppose if you put a instead of RF, if you put your DC supply, DC sputtering, and if the DC is a pulsed one, for example, pulsed means is a on off, and you can able to adjust the duty cycle. And by adjusting the duty cycle, we can optimize, or we can able to prepare our nano size material according to our requirement. There is another advantage of a pulsed DC sputtering. And these are all different types of sputtering technique. And the main advantage, the main point is, and the film quality is a build or material quantity will be very, very, very fine. And also you can able to control the size, nano size of your material on your substrate through your sputtering technique. And and another one is hot wall epitaxial technique. You may raise a question, what is called epitaxial? Epitaxial is something, but substrate is one type of material. If you take your glass, there is no arrangement. Substrate is a silicon wafer, single crystalline wafer, and the wafer is having a different plane, 100 plane. For example, I have taken a 100 plane as a wafer plane, and it is having its own d value, interplanar distance. And then in that case, what will happen? In order to make a nanomaterial in the same d-spacing of another material on the silicon wafer, then if you're able to get the material in the same d-spacing or near about the d-spacing, then that is called epitaxial. And that's why we have called as a hot wall epitaxial technique, because here through this technique you can able to have very good thinking. You may raise a question why we want a epitaxial. For example, if you measure the resistivity or conductivity of any particular material, each and every Miller pen is having its own electron density, and depending upon the electron density, the conductivity will be changed. For example, the density is more, conductivity will be more. And if the density of electron, where we can have a density of electron, if more number of atoms in a particular plane is there, then more number of electrons are available. Therefore, in a particular plane, in a particular Miller plane, we can able to have a conductivity either high or low depending upon our Miller plane. That's why we need the particular epitaxial material so as to our satisfy our requirement. Okay, another one is a pulse laser deposition. Actually, again, the whole thing, for example, your target and substrate should be loaded inside the vacuum chamber. Again, the vacuum level will be order of 10 power minus 6 torr in laboratory. In industry, the level will be 10 power minus 9 torr. And here, instead of our electric field and magnetic field, here I have used only is a laser beam. Laser beam is exposed your material. And because of the high energetic laser, and material will be vaporized. There is a bloom will be formed, and that bloom will be deposited on your pre-cleaned substrate. It's a sophisticated one, and therefore you can see the same picture. You can able to have very good uniform material of your germanium. Similarly, I have taken indium oxide, indium tin oxide. I have got a very good nano size or a very good uniform size. That is main advantage. And if you are able to have a uniform size, then property will be unique. That's the main advantage of your uniform nano materials. Therefore, it's a versatile technique, and only in selected laboratory this technique is available. Okay, and I can quickly move for the chemical route. It's a chemical. Already time is 1 o'clock nearing 1 o'clock, and it's a chemical route. Is a sol gel technique. Is a simplest technique. Even in your laboratory, and beaker is sufficient. There's a beaker and a small furnace is sufficient. Even microwave is sufficient. Even in your home, people are using microwave use as a cooking vessel, a cooking instrument, and the cost may be very, very low. And therefore, you need only beaker and air grade chemicals and some solvents. That's all, and also gel material. And for example, this sol gel process involves the transition of system from a liquid, for example, colloidal salt, into a solid. There is a gel phase. The sol gel process allows the fabrication of a material with a large variant and properties. So ultra fine powder can be prepared through this sol gel medium. How we can able to have ultra fine powder? For example, if you take our gel medium, inside the gel, some small cavity is there. In that cavity, your material will be formed. That is a nucleation will be initially formed, and slowly it will be grown and into a larger size. Therefore, in that cavity of your gel medium, and you can able to prepare you can able to have our material like that. For example, initially the process gel is then formed. This process is called gelation. For example, in the first diagram shows the gelation is a liquid form, and it will allow slow evaporation, and you can able to form a semi-solid medium. And inside the semi-solid medium, our material is there. And how we can separate out from your material? The gel is dried at a higher temperature around 100 degrees centigrade, and only you can evaporate your water and basically remove water from the hydrolysis products slowly. And then you can take it out of the gel medium and put the gel medium in a furnace, and you can remove your organic materials. Then you can collect your powder. Powder is very good nano powder. And if you spread this nano powder on any substrate, then you can able to have a thin film form. Instead of thin film, you can have a bulk film.
Hello, hello, sir. Hello, sir. Hello. Hello, sir.
I think the connection
Yeah.
is
Okay, sir. Okay, sir. Okay. So just now for 1 minute. Within 1 minute we will come.
yes, this is good. So, and
Yeah.
also it is not any urgent to follow the schedule because we are very flexible and it's 30 minutes before in the planning, and we started later, so he can finish in when he wants. So it's no problem with time.
Yeah. Don't worry, sir. We will manage with WhatsApp group. Don't worry. And also, if suppose we can extend the time half an hour. Your presentation.
Yeah, I think we continue at the 1:30.
Yeah.
So we don't need any break or so because this can be a continuous.
Yes, sir. Continue the session,
stream.
right? Yeah. Okay.
Yes, and now it's 30 minutes left, so this is fine, and then we can have a discussion, and maybe if there is time, we can introduce the first presentations addresses because they were on audio only, not the video, so we can take them again maybe.
Yeah.
So maybe he will follow link again and be in the attendee list.
I will call him. I will call him.
So for all participants, this is an initiative which was actually recently
Sir,
done.
அதே லிங்க்ல வாங்க சார். சேம் லிங்க்ல வாங்க. அதே மாதிரி வாங்க. அதுல கிளிக் பண்ணியா போதும் சார். கிளிக் பண்ண நீங்க உள்ள வருவீங்க. சரியா? Okay, sir. Right. Okay. So he will come soon.
Yes.
Yeah.
I make you host now so you can, because I think he will come to the attendee list again maybe when he enters the link. So meanwhile, we can also present to the participants that this is a recent contact which we took and initiated quite fast and efficiently. We had some technical problems, but this is a part of the Sweden and India exchange on research and innovation. So we will continue this one. So it's not only one-time webinar. So the idea is to continue. So all participants feel free to share ideas on this exchange because we can learn from each other and then we can move ahead both in research, innovation, but also make more usefulness. So I will bring up some of these things in my talk, but this is just to emphasize the purpose of this first seminar. So I'm very happy that we managed to.
Thank you. Sir, with Mikael sir, whether he will come in the panelists, right?
I think maybe he will be in the attendee list, and then you need to invite him again.
Okay, then I will set that.
So this event is a co-organization with the NANOSMAT, which is a society that is creating the conferences and now also webinars. So there will be a webinar on June 17 on this research and innovation. So I can mention this meanwhile. Now he's in the list as guest. Yes.
Sir, sir.
Okay.
Okay. 1 minute, sir. I will make you host. Okay. Yeah. Okay, right, sir.
Okay.
All right. Sir.
Yes.
Now you are okay?
But
the video is not there, sir. I can't see you.
Meeting. Video where we can have.
I think you are now not now host. I will make you host, sir. 1 minute.
Okay. Yes.
Hello, sir.
Yes. Are you able to hear?
Yeah, able to hear, but we can't see you.
Oh. Then I can have. Are you able to see now?
Yeah.
Yes.
Yes. Okay. What about slides?
Okay, sir. You just share the slides, sir.
Okay.
From the beginning. Now it's okay. No, not from the beginning.
Okay.
From the, yeah.
Oh yes, I can start from our from the where we have stopped.
Yeah, yes, sir.
Yes.
So I think it is better.
Ah.
Now you stop the share option and again you share it. Okay, now okay, sir. Okay.
Are you able to see the screen?
Yeah, yes, I can.
Okay.
Not the screen.
Okay. Sorry for the interruption. And the next one is the spray pilot technique. And here you can take your material in the form of a solution, and you can put your solution in the reservoir, and you can able to control your flow. And there is a carrier gas, and through that carrier gas, we can form the solution instead of a liquid. You can able to have fine droplets through your nozzle. And here the fine droplets will be dropped on the substrate, pre-clean substrate. Of course, you can keep your substrate at the elevated temperature. The temperature may be around 300 degrees centigrade. And here the solution is something, but it should be easily vaporized or it should be easily evaporated. And like you have to take ethanol, methanol, or isopropyl alcohol. Therefore, you can dissolve your solvent or you can dissolve your material in the solvent, and the solvent should be easily vaporized. And in addition to that, if it is not, your salt is not able to dissolve, then you can add a few ml, 1 or 2 ml of acid. You can able to form a paste, and then you can put your isopropyl alcohol or any alcohol, and you can prepare the material from the solution. You can the particular constant element will be released. Most of the oxides can be easily prepared through your spray paralysis. For example, a very good indium tin oxide can be prepared through that oxide, any oxide materials. And these are all power supply for heating your heater. It's a hot plate, and above your hot plate you can put your substrate. And whole thing should be in a vacuum hood, and it should be the unnecessary air should be evacuated through your exhaust fan, and toxic gases will be coming out from this reaction, and that should be exhaust through your exhaust vent. And that is a simple technique, spray paralysis. Instead of a spray nozzle, you can put your nebulized nozzle, and that is called nebulized spray paralysis technique. And most of the oxides can be easily prepared through this particular technique, and you can have a larger area also. through this technique. And another one is a spin coating technique. You can take your gel medium, already I have mentioned, and the gel should be spread on any substrate, and that substrate should be rotated. The rotation will be around 1500 RPM. So as the solution, it's a semi-solid solution, will spread through your throughout your substrate, and even that it should be any additional liquid, and you can pack these particular substrate. After spreading, you can remove the substrate and put it in a muffle furnace. And similarly, you have to repeat it for your requirement. And if you test the substrate material, this on the substrate, you can test the material. It will be having very uniform nano-sized material we can able to have through this particular spin coating technique. Therefore, the parameter adjustable for this one is RPM and your semi-solid solutions molarity, RPM speed, and packing temperature, and molarity, etc. These are all some of the parameters we can able to optimize, and through the optimized condition, you can have very good nanomaterial through this particular spin coating technique. Even inorganic or organic material can be prepared through this spin coating technique. This another technique is electrode deposition setup, and here again, this we need one potential set calonostat to produce a constant potential and also constant current. If it is if we fix constant potential, that is called potential static condition. And here, but the potential should be fixed with respect to any reference electrode. This is the working electrode. This is our counter electrode. Counter electrode is something but platinum electrode or graphite electrode. And this is a solution. From the solution, your constant element should be released because of your external potential, and that your ions will be deposited on your substrate. For example, sulfur, for example, cadmium sulfide, if you want, cadmium sulfide will be deposited on your working electrode. Here, the solution is something but cadmium chloride and thiourea, for example, sodium sulfide. And these two solutions, or these two salts, these two analog grade chemicals should be taken in a particular proportion, in a particular molarity, so as to have our stoichiometry in your material. And that is called electrode deposition. Here you have to keep our potential constant with respect to ACE or any hydrogen electrode or any other electrode. And that is the technique called electrode deposition. Here also we can have very good thin film. Either compound material can be prepared, either binary, ternary, etc. And the constant elements should be present in this particular electrolyte. That is very important. And that your element should, or the chemical should be dissolved in a particular solvent. For example, in your water, distilled water. That is called electrode deposition technique. And this is nothing but very simple technique is a chemical bath. This is the solution, and from this solution, the particular constant element should be released, and that ions or any particular compound will be released from the solution, and it will be deposited on your substrate. And substrate you can put anywhere in this particular solution. And in order to have a uniform coating or uniform nano material, here you can put a stirrer, and solution should be stirred continuously so that the concentration of your ions near the substrate should be always a constant one. Once the deposition is taking place, the concentration near the electrode or near the substrate will be minimized or minimum. And in order to avoid that particular one, you have to rotate your solution by putting a stirrer. And or you can raise the temperature. For example, in order to have very good nano material, you can raise the temperature. That's why you can put a water bath. Water bath can be raised up to a temperature of 99 degrees centigrade. From room temperature, you can keep the temperature constant, and you can make a nano material, and the nano material can be prepared on your any pre-cleaned substrate. And here the requirement is only thermometer, one stirrer, and beakers, etc., and the suitable chemicals for your compound. And this another one, precipitative technique. And once if you prepare your chemical, and you can have our solvent, and some additives will be added, immediately precipitate will be formed. Once the precipitate is formed, and the precipitate should be cleaned by or washed by distilled water continuously, and that precipitate should be collected. And if you dry it, then you can have a very good nano powder. For example, if you take a cadmium nano powder particle, cadmium sulfate and ammonium sulfide will be taken, water as a solvent, and some of the additives should be added to have our nanoparticles. And similarly, I have given a zinc sulfide, cadmium sulfide, zinc phosphide, cadmium phosphide, and list is extended. For example, reactive method in high boiling point also can be used, and here the solvent is instead of in addition to water, we have to have other solvent also, and that is called reactive method in high boiling point. And instead of water as a solvent, you have to take other solvent. For example, nanocrystalline cadmium selenide can be prepared by oligomeric cadmium and ethylene vermilion as a solvent. And like that, the list is extended, and here the requirement is very, very few equipments, only beakers and suitable chemicals and suitable solvent also. And reactive method in high boiling point is extended, and even you can have an indium arsenide. For that, you can have our indium chloride. You can have a very good indium phosphide and also indium arsenide nanomaterial. Even you can have a gallium arsenide, gallium phosphide. This is all semiconductor material and also high carrier mobility for device applications. And finally, we can have a combustion synthesis, and through that we can able to prepare a very good nano powders. For example, you can have a stoichiometric indium nitrate and tin nitrate will be taken in a particular proportion. For example, I have taken 95:5% and 95% of indium nitrate, and indium nitrate means nitrate will be evaporated, only Indian will be there, and indium will be in the order of 95%, and tin will be in the order of 5%. In addition to that, we can have oxide, this indium tin oxide, and like that we can have different proportion. And here the organic fuel is nothing but urea, and you can take these two as a solution form. This is a clear solution of indium, clear solution of tin, and tin is nothing but a tin nitrate, and then our indium nitrate, and then you can mix these two in a particular proportion. And here you can have a fuel, you can add it, and finally you can put it in a muffle furnace, and slowly you can rise the temperature at a particular ignition temperature. It will be blow, and after blowing, then automatically it will be sublimized. And after that, you can have very good nano powder will be there inside the beaker. I can collect the powder, and that powder, if you see the size, it will be in the order of a nano size. And how we can measuring the size of your nanomaterial is one tool is X-ray diffraction, and another tool is a transmission electron microscope. Through your transmission electron microscope, you can easily see the particular size of your nanoparticle. Here there is a scale is there, and through that we can measure the size of your nanomaterial. And the same material is in the another direction, another d value. This is another d value. Therefore, this is one nanomaterial of, for example, cadmium sulfide. This is also cadmium sulfide, but different orientation. This is also cadmium sulfide. Overall, we can measure and we can take average of your nanomaterial, and through your temp. And in your XRD, there is a peak, and due to your size of your material, if the size is reduced, the peak would be larger. Like that, we can have a different peak. From the prominent peak, you can measure the full width half maximum, and from that, we can able to measure the size of the material, size of the crystalline size. And here you can see the for example, this is a cluster of a particle. It's a combination of your particle is nothing but cluster, and in a particular particle, we can have a different crystallites. Different crystallites means the same material but a different orientation. Therefore, for each and every crystallites, there is a boundary. Therefore, that is a crystallites, and this is a boundary wall of your particle. Therefore, this size can be measured through your X-ray diffraction. Through your X-ray diffraction, average value will be evaluated, and the average value can be reported. For example, these are some pictures, and this circle corresponds to this particular particle. Therefore, through your sum, you can able to see the particle size, and through your X-ray diffraction, the crystalline size can be evaluated through your X-ray diffraction. For example, this is a single crystalline material, and arrangement is uniform. And if it is a perfect diffractometer, then we can have a delta function of our X-ray diffraction. And since it is a single crystalline, and if it is broken into small pieces, these are the small pieces, and these are all some size. We can measure the size, and the average size, overall average size will be there. Due to that average size, then broadening will be taking place in your X-ray diffraction. We can measure the broadening, and through that we can able to measure the crystalline size. That's a T is nothing but your crystalline size, through your X-ray diffraction. Lambda is your wavelength. B is the full width at half maximum. And if you want to have approximate value, that earlier diagram, you can take your B value. If you want to accurate result, and for each and every instrument is having one broadening value, and that broadening is nothing but beta to your instrument. And this B to your sample, B to your instrument, you have to subtract and take your correct value of your B, and you can substitute this B value, and you can take your you can able to evaluate your crystallite size. Here the beta B is something but your Bragg angle, and B is something but full width at half maximum of your after instrumental correction. Lambda is your X-ray wavelength. By this way, we can able to have this one typical data, and through that data we can able to measure these are full width at half maximum value, and this is a sample, and this is due to your instrument, and you can take your value, and this correct value of your sample, and you can substitute this data, and finally I can evaluate it. The value is 103 nanometer. By that way, we can able to measure the size of your nanocrystalline materials. Finally, I will come to a conclusion. Is a nanomaterial synthesis is maturing with new postulates and procedures that are being introduced on daily basis. Though many methods are available, the choice of a particular method depends on the type of material geometry required, and also the scale at which the product has to be produced. Therefore, depending upon your requirement, type or size, shape, and you can select the suitable methods, and through that method you can optimize that particular material preparation parameters. One can imagine that new synthetic stereochromy is a stereosis was involved in the feature as a requirement for any application. Size and shape of the material increases. By that way, we can able to have, and these are the two important tools. Thank you for your hearing, and any questions from the participants?
There are only two questions.
Okay.
I will allow them to ask questions, sir.
Oh, yes.
Yes, it is possible. We have in the question and answer part, there is a possibility.
Yes. Question and answer, yes.
There is one question there in the question and answer.
Yeah.
What about?
Yes, sir, there is a dip coating. Yes, sir. What about a dip coating method? Of course, a dip coating is nothing but once if you are able to prepare your solution, and you have to see very careful about the precipitation should not be taking place. Slowly you can dip your substrate, pre-cleaned substrate should be dipped and pulled out, and you can able to have a coating on your substrate. It's also another way of your nanomaterial synthesis.
And also
Yes.
in the chat, there is why the value 13.5 megahertz specifies for RF sputtering.
Yes, in your RF sputtering, you have to capacitance matching should be there in between your substrate and also your target. And here 13.5 megahertz is nothing but is a very good matching between your substrate and your target material. The distance between these two is nothing but around 6 centimeter. And for the 6 centimeter, you have to have a suitable matching. And therefore, the frequency is 13.5 megahertz is a suitable one. Okay. Any more questions?
No more questions, sir.
Okay.
No more.
Then I thank the organizer for giving me this opportunity. And also, Mikael, I also thank Mikael for extending this international webinar, and also he is also one of the resource persons. And
Yes,
yesterday he trained me very well.
Yes, this is very good to have exchange and updating and about details from different types of materials and methods and so on, because later on when we want to apply those, maybe there are some other methods which fits better for different purposes, and then other methods for another purpose and so on. So so
Sir, okay.
Yes.
So no question. I think no more question is there.
Okay. How we can exit?
Sir, another question. Sir, is the
Ah.
sputtering voltage constant for a material?
Sputtering?
Sir, is the sputtering voltage constant for a material?
No. Sputtering power we have to adjust, and depending upon your binding energy of your material. Therefore, it is not a constant. We can vary the power. For example, 10 watt, 50 watts, 100 watts, like that.
Okay, sir.
Therefore, power is also one of the parameter, variable parameter.
Okay, sir.
Okay.
Okay. Now I think question and discussion is over, sir. No other
Okay.
questions.
Right.
Sir, I am very grateful that you took the time, a very meaningful
yes.
one, and you
Yes.
try to address our group. We are all very pleased with your topic. Lot of comments
Yes.
I got personally to my WhatsApp. A very
Okay,
informative.
you can send it to my email.
It's a sure, sir. Sure, I will send it. Lot of appreciations I got, and we are.
Okay.
I want to appreciate you for your inspiring presentation.
Yes.
Your group are very satisfied with your presentation.
Oh,
Thank
yes.
you. Thank you very much, sir. Thank you very much.
Okay.
Okay,
Thank you.
Sir, Mikael, sir. Mikael,
Yes.
sir. Now the time is 1:22, right? 23.
Yes.
I think any half an hour, we give a break or continue your section at 1:30.
I can continue at 1:30. So maybe here we remind from the welcome part, because now maybe new people have entered to this presentation. So maybe we.
I think we share that videos again, right?
Yeah, the first 2 or maybe 3 videos just to share, so
Okay.
people can understand. And the aim of this webinar is to create exchange, so we can have other ideas to continue with. So this is an
Okay.
initiation, and then it will depend on the things which people propose.
Yes, sir. Sure. Then will we start our section in the at the time.
Okay.
That's good. Okay.
Yes. You can start.
Okay. Now, sir, can you make me as a host? I want to share the screen. Yeah.
Okay. Where I have to?
Sir, my right side.
Yes, your right side.
Yeah.
Yes, right side.
Top. At the top.
Chat or pin video.
No, sir.
These are the two options I have.
If you click on the participants, on the top there should be panelists and attendees.
Okay, sir. Yes. Sir,
then participants, yes.
Yeah, then you just stop the sharing, sir.
Okay. Where you have to, yes, stop sharing, then only we can have. Yes.
Yeah.
Yes.
Now you can make me as a host.
You are host now.
Yeah.
Now how to change?
He is host. I can see it in the list.
Okay. Already it is in the host. Okay.
Okay then. Now, sir, I shared the wordings of our honorable manager. Okay. And Dr. Nasar Ali. Is it audible?
Yes,
Respected Principal Dr. Vincent Joy, our chief guest, Dr. Nasar Ali,
yes, also video.
Our resource persons,
What's that?
its coordinator and organizer, Lieutenant Dr. Shaiju, conveners, organizing committee members, and beloved students. Indeed, it's a privilege for me to felicitate this very important and meaningful two-day international webinar on nanoscience. I'm so glad that it is organized by Department of Physics of Christian College, Kattakada. Last year, we had an international seminar and it had a great success too. Although the spread of COVID-19 has prevented us to come together and have a seminar, so we switched onto a webinar. We are using this as an opportunity to enter the limitless world of cyberspace and spread our wings to become smart teachers and students beyond borders. I appreciate Dr. Syväjärvi and all our professors and the whole physics department for taking this initiative to make this happen. And its subject is also very interesting and informative. Nanoscience is an emerging area of science which involves the study of structures and materials on an ultra small scale. Its motto is very interesting: thinking big, working small. Nanoscience and nanotechnology brings out drastic change in the field of food security, energy production, medical field, environment, textile industry, and cosmetics, etc. There are lots of studies going on regarding how to prevent coronavirus by using antiviral surface coating. However, we hope that nanoscience and technology will bring out some solution in this area. Anyway, I am sure that this webinar will be very effective tool and method to gain more knowledge and information. Once again, appreciate your efforts and struggles. May God bless you all.
A very good morning to
Is it audible on
everyone.
video?
My name is Dr. Nasar Ali,
Yes, sir.
and I'm
Yes,
speaking
video,
here from
yes.
the NANOSMAT office based
Here?
in Manchester in the
And here
United
also.
Kingdom. And it's a glorious day here today in Manchester. The sun is out and the temperatures are in the mid-20s. And I'm sure this is nothing compared to the summer days in India. However, we are trying to enjoy this good weather. But we are still officially in lockdown in the UK due to the COVID-19 situation, and I would like to take this opportunity to welcome everyone to this two-day international webinar on nanoscience. Now, these webinars will become a lot more important now, especially due to this COVID-19. And surely this will have an impact on the world and how we live our lives and how we conduct our businesses and how we go on about living our lives. And distance learning and doing work over the internet is going to play a bigger part now in our lives. So it's a very good initiative from the Christian College to organize this two-day international webinar on a very, very important topic, nanoscience and nanotechnology. So I congratulate the Department of Physics, Christian College for organizing an excellent webinar, and I'm sure you will all find it very, very beneficial. And now we have these good technology, sophisticated, advanced technologies platforms which allow us to conduct these meetings. Also, I would like to say a few words of thanks to my colleague, Dr. Syväjärvi, who is currently the head of the physics department. Dr. Syväjärvi I met in 2011, 9 years ago, when I was involved with and chairing a international conference on nanotechnology, the NANOSMAT conference in 2011, which was held in Krakow in Poland. and I was very pleased to meet him. I listened into his presentation, and we established a friendship. And since then, we have been regularly in contact, and I was very, very happy and pleased by his personality. He's an extremely kind person, and we know that if you're kind to others and if you do good, good comes your way. So earlier this year, when I found out that he was promoted to lead the physics department, I was very, very happy for him. And I'm sure that under his leadership, the department will do extremely well. So this webinar is being organized by the physics department, and which is part of Christian College, which is affiliated to, I believe, the University of Kerala. And it is very important that we actually, as I mentioned earlier, that we continue to work on science, because science is very, very important, and especially nanoscience and nanotechnology, which has huge potential. So even if we look at this current climate that we're in due to the COVID-19, in a lot of the countries, I know in the UK, they were saying that it's science must dictate what happens when we go into lockdown, when we come out of lockdown, and also how to overcome this COVID-19, this virus. So therefore, there's a lot of efforts now being done all around the world. I know there's groups in Oxford University, a lot of people, scientists in China, in Germany, in the United States are working on developing a vaccine which will get rid of this virus. So scientists must continue to work even though the world may be in a lockdown due to COVID-19. So as I mentioned, this is an excellent opportunity, and I'm sure the scientists will work together on very, very important topics in order to see if they can overcome some of the challenges that face us as a global community. So I wish you all the best, all the best, and I hope that you're keeping safe during these very difficult and unprecedented times. And but we need to be very optimistic, we need to be very positive, so therefore we need to have this positive approach in life and continue to work, whether that might be working from home or so, working with these special social distancing measures that we may need to incorporate in our lives from now on. So once again, welcome to this two-day international webinar, and I hope you found this very useful, very productive. And even at NanoSMAT, we are creating an institute now which will be involved in distance learning, e-learning. We have a webinar on innovation on the 17th of June. I have my colleague Mikael from Sweden, who will be giving this webinar on innovation, how you can translate the work you do in the lab scale and translate it into innovation, and to which could lead to startup companies. And Mikael will also be speaking later today on his research, so I'm sure you will find that very useful. So in the meantime, thank you very much and have a great webinar, and I look forward to interacting with you and with you after this conference, after this webinar, and also in our future NanoSMAT program.
Sir. Mikael, sir.
Yes.
Now it's a time to your presentation, or we give any break?
I think we don't have any break because it was delayed, and some people come to this time to present. And
Okay,
for those who need break, also they will be on. We will upload afterwards these presentations.
So then we start our section. Okay. Let us give an introduction and we start it.
Yes, maybe just maybe also the second video you can show, because it was also desktop. The second welcome address.
All right, 1 minute. This one?
I think on the left, most left.
This one?
The Department
No,
of Physics
the
has decided to
previous
conduct.
one. On the left,
This
number
one?
60. Yes,
A principal's address, right?
yes. I think that was also desktop. Yes.
The Department of Physics is organizing 2 days international webinar on the topic Nanoscience 2020. Nano means the particle size is equal to 10 raised to minus 9 meter. When we reduce a material in nano, the whole property of the particle changes, which means the electrical, optical and magnetic properties change. Now, the human beings are used these property changes in the various daily purposes. Now, the gigantic electronic devices reduces its size in nano forms. I congratulate the Department of Physics for organizing this 2-day international webinar. Especially, I am congratulating the faculty members and its HOD, Dr. G.J. Shaiju, for organizing such a wonderful event. Thank you.
Okay, sir.
Yes.
Now it's okay. I think let us start our session, right, sir? Now I give a brief introduction to you, sir. Dr. Mikael is conducting research in growth of advanced materials since 1995, such as graphene for gas and biosensing, and silicon carbide for new energy applications. Surface engineering and characterization are crucial for the materials developed. This is particularly important for the realization to applications. Since 2005, Dr. Mikael has gained experience in the entrepreneurial discovery process by creating usefulness, especially startups, technology transfer from research and innovation. He has experience in wider contexts such as European regional research and innovation strategy for smart specialization, especially RIS3 and strategic national innovation programs. I think coming June 17, he has a section regarding innovation. Surely I pass all the information on the NanoSMAT platform. All of you welcome to this session. We are very confident to get something new from you, sir. Another one thing, you give good support within 3 days. Actually, we planned in 4 working days only. Dr. Mikael sir know the thing. Only 4 days you give the consent. At the same day, when you give the consent at the same day, I took 2 other, my beloved sir and my colleague, I took it as a program, international webinar. On the same day, I prepared the brochure, send it. So only 4 working days, we got to prepare this international webinar. So we face some technical issues. Am I right, sir?
Yes, but we have solved them, I hope.
Yeah, then now it's so smooth. Okay, now it's going smooth. Thank you, sir. I handed over the session to Dr. Mikael Syväjärvi for the talk on the topic surface characterization and modification of graphene and silicon carbide as engineering tools. Kindly forward, sir.
Yes, thank you very much, and thank you for taking this contact to create this exchange and this webinar, and now we can have input and discuss further more ideas from these things. So this is also what I would like to initiate, and my background is research since many years, from 95, and then I have been interested in how to make more usefulness from the research, and then now I think we have an opportunity by these webinars to create more exchange, more regularly than conferences, because it's good to meet physically, but also this is one way now in these times. And when there is more need of doing things digitally to save on travel and so on, then we can also contribute to the climate and so on. And I will just introduce, for those who have been patient enough to attend this from the beginning, there were some delays and technical matters, and we have not done this before, so those we could manage to solve, I hope. And this is now also viewed on the YouTube because there were many registered. And these presentations and a summary of this will be available afterwards on the channel. We will share it in some way. So it is that is the idea. And for those who now come, we will continue this one. So if you need, you can take a break. It will also be a little bit available afterwards. But I think we continue now because there will be people coming in. So I will now share the screen. And now hopefully you can see my screen with
Yes,
the
sir.
title.
Yeah.
Okay, great. So I will now introduce some of my experiences from the research and innovation on different aspects. And I have, of course, a particular field. I don't have so broad, so one cannot cover all the different disciplines and methods and materials because it's huge. But we have a very good overview and introduction from the first talk about different materials and different methods for the different things. And at the end, depending on the application, maybe one method fits better than other ones, and for other purposes, there's another method and other materials. So it's like a matrix which we combine. Because at the end, it should be something which is used for an application. And then we need to understand the materials, but also how to measure the properties of this. So the instrumentation part is really important for the application, because for the research, we can have some information and then we publish the findings. But for the application, then we need this as an engineering part, instrumentation, so we have reproducibility of the materials. So that's why this instrumentation is very important for the usefulness in the application part once it has matured from the research. So I will talk a little bit on that part, on the characterization and instrumentation for my materials, which we have been growing, and those are graphene and silicon carbide. So I started with research a few years ago, and I'm from Linköping University in Sweden. And actually, in Sweden, we have, when we enter a program, because I started my program, Applied Physics and Electrical Engineering, in 1989. So that's my first background in this field. And then the tradition is in Sweden that such programs, they have this type of overall. So this is the size of the overall when I was a student. And that was many years ago. But I have applied physics and electrical engineering as starting point. And my method, which I'm using, is physical vapor transport. And this is for the growth of silicon carbide. And the basic principle is that you have a source, like a powder, which contains silicon carbide, but in polycrystalline form. And when we heat up that one, it sublimes, and the vapor species are transported to the growing crystal. And then we grow a crystal and evaluate the material and so on. So in the 90s, when I started my PhD studies, then silicon carbide was very immature No one knew about the most optimum processes and so on. So everything we did was new. So it was a global interest in silicon carbide as a material for power electronics. So it was a motivation for that. But from a growth point of view, there were many new things. And my particular involvement is in the sublimation, this type of method, which is illustrated in this picture. And the aim is that we grow a crystal and then we cut out wafers from that, polish the surfaces, and then that is used for epitaxy and then for surface engineering and so on for power devices. So this is the aim of that particular method. And now silicon carbide is commercially available. You have wafers which is 6-inch or even soon 8-inch is available on the market. And the power devices, they are a business. But it took 20 years to go from this materials point of view to a market. And this is similar with the things we are doing now, because we make some new processes for the nanotechnology and we characterize them and so on. So it will take maybe 5, 10, or 20 years before they are on the market. But once they are on the market, they will make a bigger impact in some key enabling way. So it's a key enabling technology. So this is the one of the outcomes of the nano. And in my PhD, we modified the method. So instead of a long distance from the source to the growing material, we decreased it, but then we could use the growth rate and we can make an epitaxial method to make thin films, which actually were thick films for the silicon carbide, because to convert 10,000 volt in the power devices, you need thick film. So that was the aim of this method and my PhD thesis, to develop it further to make thick films on silicon carbide substrates. And here is an illustration of a wafer with a film on top of it. So we managed to develop the process to achieve the growth and thick films. And important features here were the characterizations. So we used different methods which were suitable for the silicon carbide to characterize the material. And one of them is photoluminescence. So once you have good quality material, you have certain characteristic peaks of the phonons, of phonoreplicas and so on. So once those start to appear, then you know that you start to have good quality. And when you explore these things over larger area, so you have uniform quality over a larger area, then you can use the XRD. So from the rocking curves, you can see that the peaks are narrow enough, so you have good quality. So these are extremely important characterization tools as feedback to the growth. And all the time we have been doing material development, we need the feedback to the growth parameters and so on. So this is a loop of the different things. And since you are using the surfaces, there are some characteristic features of the silicon carbide that when there is growth, so it's layer by layer growth, step flow growth, then you start to have steps and irregulations of the steps. So those we have studied a lot to understand, why are these steps not straight? Why are they bending like this and so on? And how can we modify the growth conditions to tailor these ones? And some of the samples, when we had the possibility, we also did the high resolution TEM to study it on the atomic level to see what is the quality. It's very narrow, small area, but then we could see the get some feedback also. So there are various methods which we have been using: TEM, AFM, SEM, and then XRD, photoluminescence, and various tools as feedback to the silicon carbide. And particularly these, the surfaces, when there are steps, That's very interesting because basically that is a defect, but it can also be used. I will show this later when I talk about graphene nanoribbons. But we need to understand them, how they form, and then how can we control them. And the basic mechanism is that you have small steps, and then they bunch together to make larger steps, and then at some point there will be a big problem because you cannot control the growth anymore. So this atomic mechanism is really important for these understandings. So that was a part of my PhD thesis, to develop a high growth rate of silicon carbide and study the process and the structural quality of these materials. And in the 90s, it was very much new, all avenues. So I focused on the growth. So I had my PhD thesis in 1999. So that is now 21 years ago. So time has been passing. But for the intended purpose of these thick films to convert 10,000 volts for the power devices, we had nice films. They were thick, smooth surfaces, and the structural quality and so on was nice. But the layers were not pure enough to convert the power. So it was actually the method, and this material was not useful for the power devices. So that was the highlight of my PhD thesis. Developed a process which was not useful. Yes. So that was not very good at that time, but of course we wrote papers and so on. And then from the innovation point of view, this was an original idea that we could use this process and these materials for the power device. But then a few years later came one researcher from Japan who had a new idea that I want to use silicon carbide and I want to introduce certain elements to the silicon carbide, because then you can have light emitted from the silicon carbide. So silicon carbide as a light emitting material. And for this particular LED, for a white LED, he needs thick layers. So then it was a method with he needed for that. And then I was, I have a method with thick layers, which I have been developing. So maybe we can start to collaborate. So this is Satoshi Kamiyama from Mayo University, who came up with this idea, but they don't have so much silicon carbide experience. So that's how we started the collaboration. So then this growth became also relevant again. And I will not go into the details because there are so many different things. I want you just to get the flavor why the development of material and processes is always important. If not now, it will be relevant later on, like in this case. So the idea is that when we dope the layers with silicon carbide with certain elements, we get luminescence out of it as a broad peak. And when we do this in 2 layers, we get 2 broad peaks. And if you do this in a certain polytype of 6-stage silicon carbide, the 6-stage silicon carbide, the light comes out in the visible region. And then it's a pure white light. So that was the idea. But so that's how we came into new research avenue. And then there are many things about the growth, how to handle that, and measure the luminescence from the materials and getting other feedback and combine it. So it's a big mix of different information, which now is trying to be put in place. But that was really nice because then it was a new research avenue to study the silicon carbide for light emitting properties. And the colleagues at, when we have, this is what we want to achieve, to understand on the growth and material, how the light emission can take place and not be destroyed. So there are many things to study here. And then we always need a different characterization methods as a feedback to all these things. So it's always big loops. And this is the original idea came from Mayo University. So this in this picture, you see me on the right side, and then Satoshi Kamiyama, and then it's Isamu Akasaki. So this group, he got the Nobel Prize in the blue LED 2014 together with colleagues. So this collaboration is very prestigious, so very nice for me, because I'm a simple guy from the countryside, and then in some way we came into new collaborations, and you see that there are other people also involved in these activities from Denmark and Germany. So it became very nice research avenue. And that was not the plan from the beginning. So this is what I consider as a innovation development. So if we do some things, we can have the idea that I think this is good for this purpose, and then maybe it's not, but then it finds another avenue where it can be useful, which we cannot predict. So that is also why meeting people is important, because at some point we meet someone who explains some things, and then we understand, oh, maybe we can try it for these new avenues. So the webinars are related to these possibilities to trigger inspiration and exchange, so we can create new opportunities in the research and innovation things. So there are some materials, so light coming out, but there is still far from efficient. But all these enabling technologies, they take many years. So that's, and also with the Hayano in the Denmark Technical University, we have some demonstrators and collaboration. So this is still ongoing. It's of course very much depending on funding. So if anyone knows a funding agency who likes this type of research, then send them to me so we can have money to continue to explore this. Funding is always difficult for these things, but it's exciting and it triggers new things. And let me mention another avenue from the silicon carbide point of view. In the growth, we have silicon and carbon. So we're trying to combine them to grow the silicon carbide. So that is for the growth. And when we initiate this growth, we get vapor species and they leave the surfaces and continue to do some things. And actually in one way, when we heat up silicon carbide, actually a little more silicon leaves the surface than carbon. So if we are making a wrong growth process, there is graphitization of the surface, which is very bad for the growth. But that's how we came into an avenue of making thin graphitic layers on silicon carbide using this process. So that was done year 2000, 2001. We started to explore thin graphitic layers on silicon carbide. And it was by curiosity we started to look at this process, because graphite can be interesting. And then we use high temperature to initiate this process for making thin graphitic layers. So there were some results, collaboration with Chalmers, which show that these thin graphitic layers, they have very high quality. So it's almost like natural graphite. So there were a couple of publications in collaboration with Chalmers. And as curious researchers, we continued to explore the process, and we made the graphitic layers thinner and thinner and thinner. So actually 2005, we had one layer of carbon. So very thin graphitic layer, but that is actually the graphene. So we had that result, and we asked some people, can you simulate the high temperature process so we can maybe understand more? But we did not know what to do with this. It was curiosity, and graphene was not hot at that time. But from the growth curiosity point of view, we start to explore this. And then there were young students coming to do the master thesis works towards this avenue. So we further explored the process and started to have it more reproducible. So 2008, there was a diploma student, and then after these years, then we could actually demonstrate very high quality of the graphene on silicon carbide. In collaboration with Chalmers, it was shown about quantum resistance standard. So once you have those properties, you can see that it's a very good quality material. So then the feedback from the more complex characterization tools was very useful, because graphene is one layer of carbon. We cannot see it on the surface. So we need other methods which indicate that they are there, but you cannot view it directly by naked eye or even the microscope or SEM, because then what we see is the surface of silicon carbide, but not the graphene on it. So then we need other ways to see what is there. And getting one layer of carbon over a large area is very difficult. And then these steps are again important. So the learnings we had from before in the growth about the steps, how they appeared and so on, this became useful now when we started to use these for the graphene on silicon carbide. So then these 10-year-old studies became relevant again for the graphene. So all the initial characterization and competence we are building up, this is useful maybe now or maybe later. So nothing is wasted. So I encourage students to continue to explore these things, because they will be useful in some way. And maybe it's not the learnings that you are using directly, but your competence in these things that you have gained skills to interpret, that will become the valuable things for the things in the future. And of course, there appears many different things when we start to look at the surfaces and the graphene and so on. And we have domains of the graphene on the silicon carbide. So these are just some illustrative images of how it can look like once we go into the details. But then the surface characterization becomes very important. And then we study different things, like different types of silicon carbide. How does the surfaces behave, and how can we measure them? And if we use different temperatures or different other conditions, what is happening with the surfaces? So then we started to have a picture of those things. And then we have used AFM a lot to understand the surface features. And one layer of carbon, the graphene, is useful for some certain type of applications. Then it's a two-dimensional material. I was mentioning before about the steps. They are basically a defect which emerges during the growth. So it's not very good, because it creates non-uniform surface, which makes it more difficult to process for different purposes and so on. But also, if we use these steps and try to make graphene on it and modify the process further, we actually get carbon along the steps. So then we have a one-dimensional carbon material. So this is nano ribbons. So then we can use the defects of the surfaces, the step bunching, we modify it for this purpose. And then we have another type of graphene, like nano ribbons. So that also became a new avenue, and we can use the learnings from the silicon carbide time for the growth to go into these avenues. But it was not the plan from the beginning, because we wanted to get rid of the steps to make flat, perfect surfaces. But sometimes perfect is not the thing which is the useful for different application. So this is an example of that. And my colleague, who was my supervisor in the 90s, she is the one who initiated this studies towards graphene and collaboration. So Rosita Yakimova is leading this research, and we have been working together since 1995. 14th of February at 9 o'clock, we started to collaborate. So that's many years of nice collaboration. So I expect also here that we now start a 25-year collaboration forward. So, and then we developed the process for the graphene, which is our particular niche, high temperature process. And as you know, graphene is very interesting from the scientific point of view, but also you have larger programs which now try to push the research to go to industry. So it's in Sweden, there's a national push, like a strategic innovation program, which started 2014. And then in 2015, it was a little bit more pushed to explore the material. So there was different material actors. They were encouraged to do more. So the graphene users could have a little bit more reproducible material. So that was one of the good things about being involved in a national program. It supported the interactions, and that we were started to think about how to make more reproducible material. Because that is not used for the publishing mainly, but if you have a reproducible material, then we can use it when we study the applications. So that became into another avenue of thinking. So that's when the research and innovation went into the innovation industry exchange things. And also at that time, we were also came into collaboration about using large synchrotron facilities. So this is in Lund. So this, you see this picture of the synchrotron facility with the ring, and you see some cars and houses at the end, so you can imagine how big this is. But this is used to create electrons which reflect on the surface, and then you can understand the characteristics of the graphene, one atomic layer, using this tool. And this is not something you have in your home lab and so on. So then the instrumentation and the use of infrastructure also became very relevant for this to move ahead with these things. So we have been collaborating with this both for the research but also for the industrial type of material, the graphene on silicon carbide. So then other types of infrastructure became important in order to move ahead. So this is an illustration of that need. And we had also support for the industrial activity to use such facility, because it's not very easy to get beam time. So then the national programs, they facilitated exchange in these things. Otherwise, we would not have done it on our own initiative, because it's difficult to get beam time, and it's very complex matters how to measure these things. So we needed the expertise at the infrastructures to be able to do these things. So that was, and then we could see some features. And at that time, it was 2015, we had some adsorbents on the surfaces. So they are like contamination. And then we started to understand their how they get there and how we can remove them by post-treatment and so on. So that insight came from that study using that facility. And also what we are doing now is that we have the graphene and we modify it in different ways afterwards. And we have actually one collaboration with India, Sweden, India, which was initiated 4 or 5 years ago. So Priya Kaushik has been a visiting researcher with us 4 years now, and exploring how can we use ion irradiation to modify the surfaces for different things, because the native graphene, it is useful for some things, but in other cases it cannot do. And especially if we want to see the gas sensing or biosensing, then we need the functionalization of the surfaces. So this is one way of using different ions with different energy to modify the surfaces. So she is now leading this study. And then we explore again the surfaces, what are the properties, how do they look like, and we study exposure to different gases and so on and see the responses. So we start to understand a little bit on the mechanisms, what can be happening, and see where we can use these things for. So Priya is doing that and focusing on that activity, and she's doing really good, and I'm really happy about this Sweden-India collaboration which emerged thanks to her visit. And actually this morning we had a paper accepted which she was working on. So before this webinar we had one more paper in this topic, so she's doing really good. But that's all the things came from the growth, and we understood some things and then came into new avenues and new collaborations over time. So these are some examples what can happen when we are doing the collaborations and exploring new things and get ideas from other people. This ion irradiation was not our idea. It came from Priya because she had background there and knew the people, and we could use the facility. So it came as an opportunity thanks that we were meeting. And then we can study this in different ways for other, like there are different types of silicon carbide. We try to understand that how can we use this on these things and combine. So it's like a matrix of different things where we try to find avenues which are useful. And the avenues which are useful, it will not be on the materials point of view, it's on the collaboration point of view that some people start to explore the application on these materials. And if we now change to the thinking, because research and innovation is one initial thing, and then we start to collaborate on characterization, and then some device making, and then it will be system later on. So in the beginning, the acceptance of groundbreaking things is very high. So there's a readiness level, which is, people think graphene is very exciting. So if you imagine 10 years ago, it was a big hype in the graphene and people got interested in these things. So, and it was breakthroughs every day. But after some time, it became saturated because we cannot control the findings to make devices in a reproducible way. So the maturity of technology also needs to, that's why it takes so long time to go from the initial research from the material to any usefulness of application. But once we are thinking about these things, we should also be aware and maybe create opportunities to move in those directions. So that's why 15 years ago, I started to become interested in commercializing our findings. So then we started a graphene company and we made some technology transfer in another avenue. But if we look at the bigger picture, then the regional things become relevant. How can we fit these things into a regional level, into a national level, and also international level? So that's when I started to think about these things. So the forthcoming webinars, these will discuss some of those things, how we can share ideas and experiences to move ahead in those directions. And just again, it will take many years before there's any usefulness from the findings we are making today. And this is an example which I got from Professor Amano at the European MRS, Materials Research Society meeting. He was talking about and he's one of the Nobel Prize winners for the blue LED, which led to the white LED, which is now used in applications and making a huge energy savings. So he was talking about that, and then actually the first research was done in 70s, by Isamu Akasaki, who initiated some research avenues, got interested in this material, and Amano came as a PhD student for contributing to the next things. But it took more than 30 years from the material to what we have today. So 30 years is a long time. But now it makes a substantial contribution, and there are now investors and governments who want that this happens again, but not take 30 years. So he told at this presentation that, oh, this first, it took 30 years, and now the investors want us to do more of these things, but they want it in less than 10 years. So this is now the request from funding points of view, investors and agencies and so on, to make it in less than 10 years. But it's very difficult to make these things in less than 10 years. But now they try to decrease the time by actually encouraging students who want to become entrepreneurs to move in those directions. So the academic track is not the only way. There are also other ways to make career. So you can do entrepreneurial research. And if you have an innovator type of mentality, you can do those things. So now they encourage those things in different ways. Some people can continue the basic research because it's their focus, but other people want to do these things. So then they facilitate by those programs how to decrease this creating of technology from innovations and from the research. So this was a very nice example that they actually do this in a focused and strategic way. And also in Europe, there's a graphene flagship. So European Commission has taken 1 billion euro. They put it into a graphene area, and it's called a flagship. And it started 2013 with this flagship idea that we put a lot of money so to push how graphene can move to become useful in the society. So here is a panel which was at the conference 2012 discussing those things. And now if we look at the clock, it's 2020. So 8 years has passed, and we cannot buy any graphene product on the shelf. No electronic device, no sensor or something. There are some sports things, but then graphene is added to another matrix. So already 8 years has passed for the graphene, and there's a lot of support in Europe, but also like in other countries, there are programs for the graphene and so on. But whatever we do, it will take time, and we are talking about years. So this is another example that we have to be patient with the things we are doing, continue to move ahead, and then opportunities will appear. And this is the plan. 2012, they showed this roadmap, 2013 to 2023. So now we are more than halfway through of this graphene flagship plan, but still there is not anything which you can buy. But maybe 5-10 years from now, it will be available. Maybe 10-15 years ago, you can buy it as simple as we can buy white LEDs today. But it took a long time before it became volume availability and made a big impact. But this is the field we're working on in the nano. What we create is pushing in these ways. So we should remember everything we do today is fantastic things. We just don't realize it immediately, but they will be useful in some way, either the material or our competence. And in Europe, you have that the regions should focus on areas where they're strong. Then they should collaborate with other regions to create more usefulness. Because from the materials point of view, you have the characterization, device, and system. And then that's basically a value chain. So what we are doing is establishing value chain. So our part is maybe here, but at the end it will be a value chain in technology. But for the regional growth and the national growth, they also support things, but at the end, that is also a value chain. So these things we should synchronize more, so there are synergies between the technology type of people with the regional people, and we can make more things together instead of having two tracks. So this is why I'm talking about this regional development things, and this is now European Commission is pushing for this. So these are tools which are used, and there will be money going into those things. And now that is regional things in Europe, and the regions in Europe should collaborate. But next level is that there will be international collaboration. So then the Sweden, India possibilities or other things, the international ones will be very relevant for also these things. So then we can combine these things and collaborations and value chains into other avenues. And here is one of my personal thinkings ahead. Like in my case, we have a lot of graphene materials, competence and learnings. And we had this national program which was supporting that we have industrial material available with a little more reproducible characteristics than only in research. And there is startup and innovators experiences. But like in my field, we are not experts in, for example, bio applications, because there can be healthcare applications using the graphene and so on. But there I have seen that like in India, there's a lot of activities, and the driving force for doing these things is much faster than in Sweden. So now we are initiating these things. So from my point of view, in Sweden, we have a platform from the materials point of view, and in India, there's our platform. And now we can try to match these things. So this is one of my personal focus areas where I want to do contribution and hopefully collaborations. But that's a natural matching between Sweden and India. So that's why I have been during a few years now working on relations. So this is another opportunity to build relation. And that is one of my experiences. And if you want to read more about our research, we have a homepage which makes things visible, and the Sweden-India platform is also being presented there. And the aim of this presentation was not to go into the details of the different instrumentations and characterization tools for the nano. It was to give a flavor that from the materials which are fabricated in different ways, we had some examples from the first talk. They can be in a bigger picture, and this is what we all do together. But at the end, it is people collaborating together. And if people want to do something, then things will happen. The materials and technologies will not collaborate themselves. So it's we who are doing these things. So that was my presentation. And now I think it's time for questions if you have on this topic or any things which you have in mind. So either in the question and answer chat or in the participants chat.
All of them thank in the question panel, sir.
And here is one question: if we can use reduced graphene oxide instead of graphene. Yes, of course. Graphene on silicon carbide and graphene flakes, they have certain properties, but maybe they are not suitable for other properties. And I have one of my collaboration partners is working with graphene oxide for water purification and so on. So then the graphene oxide is much more suitable for that particular purpose. At the end, it will be different types of graphene, and they can be further modified for certain application point of view. So there's not only one material which is suitable for this. And then there's a question on graphene metal oxide. I think maybe that is related to if there's a possibility of combining things. And I think this is because graphene itself may not be suitable, then you need to combine it with other materials for some intended purposes. So the combination of material is something which is new avenues.
No questions. So one question is there, sir. It's purification regarding.
Dye removal. In the particular process I was talking about with my colleague, it's for heavy metals. But then, of course, it can be explored for other purposes, but probably needs to be developed further. So if there are any ideas, we can try to match the need with the material fabrication and twist the material for this purpose. But that needs to be explored in a collaboration way. So if the material knows what is the need, we can see if it makes sense to try to explore in that avenue. Sometimes it's not, there's no particular property which fits, but sometimes we can modify the properties. And then for a question mentioned about bioapplications of regional economic development in India, I think I'm not working with the bioapplications, but what is more and more needed is that you have possibility of measuring things in a more simplified way. And like with the graphene, then you can have portable devices which do not need to be generated, have power in different ways, so they can be movable. And then they should be, of course, be connected via artificial intelligence and different ways to interpret, to get the feedback and interpret in different ways. And like in Sweden, there's a certain type of situation in the society and so on, and we have not so many people like in India. Like in India, you have much more differences. So the combination of Sweden and India could be very useful to realize what is the need actually. So I've been traveling in India a few times, and then once I was there and traveled, I understood things. And then we can see what is the particular need. But for bioapplications, I think the healthcare feedback combined with digitalization is something which can be very useful. Its application in physical world, it's very general question.
No question is there, sir.
But if I take graphene or silicon carbide as application, then I think that the silicon carbide is a very good template because it's robust, and you can make the graphene, and then you can measure any electrical change or resistivity change. But then you need to tailor the surface for gas or bio. But then you have a device, and maybe it can be self-sustainable. So you have many devices which are portable, and then, for example, gas sensing. If we would have a sensor which can detect the gas exhaust from cars and so on, we can place it in the city on many things, get the feedback, and then we can direct the traffic when there's too much pollution here, we can guide them in other ways. And this could be thanks to the sensors which are available and which measures a smaller quantity or very low concentrations, because the graphene is one layer, so then you can be more sensitive on the atomic level using the graphene, and then it's portable and so on. So that's one of the applications in the physical world which we have been envisioning from the materials point of view when it comes to graphene on silicon carbide. So that was some questions and some answers. So what now I think this is the first day session program formally is done, and we can emphasize again that the idea of this was to initiate the first exchange and as a webinar, and then we follow up that and see what can be done as next steps.
Okay. Hello, sir.
Yes.
Yes.
I think there is no other questions. Right? Yes, sir. If any other questions, we will collect in the feedback form. I will send it to you, sir. Okay, sir.
Yes.
Any other questions or any questions regarding graphene and silicon? Surely I will send you the good questions to you.
Yes, and
I will collect, right?
And also if there are like other ideas of collaborations in the different disciplines, then we are happy to exchange on the ideas and see what we can do to move ahead.
And when you show your younger your photos, and you are in young photos, I think around 8 years back, 12 years back, research photos, surely stimulate our younger researchers to do something new.
Yes, and I can also mention there that sometimes we don't know what is the new, and sometimes the young people have the ideas, but then maybe some professor says that, oh, that was done many years ago, but it doesn't mean that it's not relevant today, because there are new things which have come up. So maybe it becomes relevant later on to do these things. So even if you get the feedback that this was done before, it doesn't mean that it doesn't have a relevance now. So I encourage the young people to continue to believe in their ideas. And if you like your own idea, do more of those, because then you will be excited and you cannot sleep due to all the ideas you get from these things. And then different opportunities will appear. And since we are having the examples that whatever we do, this takes many years, 8 years, 10 years, suddenly like that has disappeared. So the young generation is really important to continue to do these things.
Sir, I will maintain this WhatsApp group even to after the session or after this webinar. If new platforms or any other collaboration works, so kindly send to me, sir. Then I will transfer this to these WhatsApp groups for the young researchers and young teachers to do something for the new, for new things.
Yes.
So kindly share your efforts, your platforms, new innovations, some promos. Kindly transfer, sir, please.
Yes, I will do that.
Okay,
thank you.
So we can do something, a collaboration work with Indian student.
Yes.
Indian student, young scientists, we can do some collaboration work, sir. Okay. Sir, what about Sanjeeviraja, sir? Is it right, sir?
Yes, a nice presentation. Really, I appreciate. Yes.
Yeah. Yes. Now I
Actually,
conclude.
we started our research only with the collaboration only. Without
Yes, sir, sure.
collaboration, we cannot. The success rate will be less.
I actually experienced your collaboration, sir. I remember that one
Yes.
with
Yeah.
other countries. I remember
Yes.
from Korea. So actually, it is gives some stimulation to initiate this type of works.
Yes. Instead of telling nothing is there, you can start your collaboration and you can begin your research in fruitful way.
Sure, sir. Yes. Okay. So shall we conclude this section, sir?
I think
Yes.
so. So once again, thank you very much, and also for NanoSMAT to support this initiative, because it came from your earlier, when you met 2011, those things.
Okay, sir. Nice to meet you and nice to hear your talk. Actually, we are very grateful to you, sir, because you give all the innovation techniques and everything regarding graphene and silicon, and you initiate our younger researchers to do something new for the society, for this nation. So some innovation mind you develop within this short time, sir. So please accept our sincere appreciation for the outstanding presentation you made.
Great.
Dr.
Thank you very much.
Dr. Mikael Syväjärvi is from Linköping University, Sweden, presented a wonderful, very informative and effective talk. Now I extend my hearty thanks on behalf of Department of Physics, Christian College, Kattakada, Kerala, India. Thank you, sir.
Thank you very much.
Okay, thank you very much. Okay, I next also I express my thanks to the chairperson of Dr. Nasar Ali, NANOSMAT, because his contact helped me to meet us. Your friendship, surely we will keep in touch. At the end, we can make a plan for new collaboration works. Surely we will ready to take that steps. Now the conclusion, now the section is over. Tomorrow section will start at the right time of 11:30. First session. The session will be 3 p.m. to 4 p.m. It will be in Google Meet. I will send all the details to our WhatsApp group. Actually, we have, Mikael sir, we have 3 WhatsApp groups, Nanoscience 1, 2, 3.
Okay, yes.
Yeah. So we encourage all the participants, registered participants, to hear your lecture and they can utilize it. Therefore, I think most probably all of the most of the participants, they watch the program via YouTube link. I think so.
Yes, I can see it was, there have been
And now,
people.
now it's a low number. The starting it's around 180, 82 like that. Okay. Because of some range problem, whatever maybe, most of them they use YouTube like. So, sir, very thankful to all the panel members. My Professor C Sanjeeviraja, sir, thank you. Thank you once again. And also thank you to Dr. Mikael, sir. Very thankful to you. Sir, now shall we conclude the section, sir?
Yes, we can conclude now. So.
Okay. Okay. See you, sir.
Yes, and now we are finished. Can you make me host?
Yeah, sure.
I will stop the YouTube streaming.
Oh, yes, okay.
But I think I need to be host.
Yeah. Yes, sir. Now you are
Yeah.
the host.